and thanks for this great opportunity. I'm very happy to talk to you about some things I've been working on since 2 years now. Does it work? Can you hear me in the back? Awesome. Did you get the handout, or should we plan it now? The handout.
Is this homework, Elia?
Yeah. No, it's not homework, but.
Is it a quiz?
Oh, for the full audience, yeah. Oh, thank you so much. Yeah, okay, there will be some time. I was planning to show to you some figures that you could then bring home as a souvenir. So hopefully we'll get those. So I'm supposed to tell you about. So let me know if it's too low, by the way. About positive geometries. And canonical forms. So being partly a physicist, I'm going to be much less rigorous than Francesca, and sorry for that. But my goal for today is to, give you a definition of positive geometry, and then give you a bunch of examples and different flavors of their appearance. So positive geometry is a fairly recent area of mathematics, and in fact we don't even agree, I think, on the very definition of positive geometries. So today I'm going to give you one, the oldest, and I guess currently still the most used. But I put in the references in the handout that hopefully you'll have soon. Also the reference for this new definition, relatively new definition. So let me start with a very short motivation from physics. So Francesca already mentioned this, but I guess it's not too bad if you hear this almost twice. So from physics, the setting we're interested in is that of scattering of particles. And the objects we are interested in are called scattering amplitudes. So here I have n particles. And these Pn are real vectors in some space-time dimension. We believe that these should be 4 by our perception of reality. So we have n particles scattering, and then something very complicated happens. And how usually, so by the laws of quantum mechanics, given a configuration of n particles scattering together, we can just say how likely it is that this process is happening. And I can really compute from this just a probability. And the probability is some integral over a function an. So an is the scattering amplitude. So n is the number of particles, and it depends on this momenta of the particles. So this is a very, very, very complicated function. And what we do to compute this is to model this complicated blob as some interaction which depends on the parameter g, which we call the coupling constant. So g is telling us how strong is the interaction happening in this blob. And if we take g small enough, what we do is that we expand this amplitude as a Taylor series in g. So from L equals 0 to infinity. So this is very formal, because often in physics this doesn't even really make sense. This has 0 radius of convergence often. But concretely, we compute this ANL, and then we can hand in these functions to experimentalists. And then experimentalists can actually measure at the Large Hadron Collider how likely it is, or they can compare this theoretical result with the experimental result of how likely it is. If I scatter 1 million times 8 gluons, how likely it is to see exactly this process with that configuration of momenta. And the standard procedures to compute this A and L, so these themselves are also very complicated functions, and they involve an integration, which is often it's a very difficult step in computing them. And we also compute them by an expansion into so-called Feynman diagrams. So this Francesca mentioned, we have some rules depending on the theory we consider that is telling us the set of graphs we want to expand on. For each graph, we associate a rational function of the PIs, and here I have an integration over product of L, what we call loop momenta. Smaller. So we have a rule for every quantum field theory on which set of graphs to consider, for which we can build, so to each of those we associate a rational function, and the further step is to actually integrating these rational functions, and then we get a very complicated functions of the PIs for each fixed loop L. So for L equals 0, there is no integration, and we are talking about a rational function. The amplitude, the biggest contribution in the coupling is a rational function. And I think this will be relevant for the upcoming talks. I think we'll be mostly talking about rational functions. But to the higher corrections, which are very relevant to physics, arise from also computing this integral, which is, again, very complicated, and people spend a lot of time in trying to perform this integration. And the role of positive geometries is that this should be equal, again, to some integral, but now, still of a rational function, but of some positive geometry of rational function coming from positive geometry. So I can replace quantum field theory, these Feynman rules, I can replace them by a geometric construction whose output is also a rational function and completely bypasses this computation. So connecting to Francesca's talk, if I take a very specific theory, n equals 4 Wei-Liang-Mills, not directly too connected to reality, unfortunately, but a very nice theory, then this is the amplituhedron. And this is called the canonical form. And now I'm going to explain to you what are canonical forms, what are positive geometries. But from the amplituhedron, you can find the same information you would get from these Feynman graphs. That is a more standard construction in quantum field theory. Okay, having said that.
But is this equality like proven, or is it conjectural?
Oh, this is super informal, in the sense for certain theories we have a construction that may work, is conjectured to work for certain n, for certain L, and we don't even know if A is a positive geometry. I mean, it's very, very informal. What I think is relevant for the following talks is that in n equals 4 Wei-Liang-Mills we have the amplituhedron, for which we believe this is true. And then there are other interesting theories that Carolina and Nima are going to talk about, scalar theories, for which there is a different positive geometry, I think simpler, because in that case it's just a polytope, for which a similar statement is true. So this is a case-by-case equality with many. Okay, now I'm going to give you the definition of a positive geometry.
Sorry, I'm just saying that's why it's good that we're not settled on a definition for what these things are, because we probably haven't found the right one.
Right.
The right one should encompass everything, hopefully.
And I'm going to give you one. The first one that appeared, I guess, in the literature and was motivated by the amplituhedron construction. So I'm going to give you a definition. This involves many ingredients, but in parallel, I'm going to give you an example that should illustrate step by step the whole construction. And please, I didn't say this, but feel free to ask questions whenever you feel like. It should be quite informal, even though it's recorded. So I have certain ingredients. The first ingredient is a complex projective variety. So what is a complex projective variety? You can think locally it lives in some complex space, C to the n, and it's cut out by the vanishing of equations, particular homogeneous equations. So my example is going to be the complex projective space of dimension 2, which according, if you go back to, if you wrote down the definition of Francesca, is the Grassmannian GR13, is the space of lines in C3. Okay, but locally I'm going to think of this space as C2, and in particular I'm going to draw the real slice of it, the real 2 plane. Okay, so there are some technical conditions, just to let you know. If you don't know these words, never mind. So X should be irreducible and normal. Okay, I'm not going to tell you anything about these technical conditions. The other ingredient is very important, is so I'm going to denote by this the space of real points of X. So X is cut out by the vanishing locus of homogeneous polynomials. I'm taking these polynomials to have real coefficients, and I'm considering the real solutions to these equations. So in this case, XR is real projective space, which locally looks like R2. Locally looks like the blackboard. So inside this space, I have this, which is a semi-algebraic set. The semi-algebraic set is cut out by polynomial inequalities. So now I'm going to draw here, I'm going to choose a semi-algebraic set. I'm going to draw some curves. These are vanishing of polynomials. So this is the vanishing of 1 minus x squared minus y squared. And this is the vanishing of y, where coordinates x and y as usual in the plane. And my semi-algebraic set is going to be this region here. This is cut out by this polynomial being greater or equal than 0, and this polynomial being greater or equal than 0. Okay, here there are also some technical assumptions. Actually, one should be regular, whatever this means. Right, and then I want this to be oriented. Actually, I have to define the interior of this set. Is an oriented manifold. So I want to give an orientation. The interior of this thing is, its interior, but defined by the strict inequalities in this case, and I'm taking an orientation on this set as a smooth manifold in R2. Okay, and now I need another ingredient, which is the algebraic boundary. The algebraic boundary is defined as the Zariski closure of the boundary of my semi-algebraic set. So what does this mean? Is that I take the boundary of x greater or equal than 0, which is this, and I take the Zariski closure. That means I take all the points on which this polynomial vanish. So I'm extending the boundary, these two curves. So maybe I should have chosen a different color, kind of purple. So this is my algebraic boundary. This is the union, and I'm going to write it as a union of more components. And this case is a union of a component C1 and C2. The vanishing of the circle and the vanishing of the line. Okay, now I have all the ingredients to tell you what is a positive geometry. Is it readable if I keep going here? No? So we say that x greater or equal than 0 is a positive geometry. If there exists a unique form, so a top form oriented manifold, here I need the dimension of dimension m. And m should be the same as the dimension of x. So x. So I'm considering a differential form, top form, on the space of x without the algebraic boundary. So here, x without the algebraic boundary would be P2 without the vanishing locus of, without this circle and without the line. So this
is complex now, right?
And this is complex, yeah, this is a very good point. So
four-dimensional real map.
This was real, and that lives in some subset of some subset of C2, or a smooth subset of C2. But it satisfies certain specific properties, which are that if m is equal to 0, if the dimension of my space is 0, then both x and my semi-algebraic set are equal to a point, and the form is actually, let me specify like this. The form of a point is defined to be plus or minus 1. Yeah. And the plus minus is the choice of the orientation on my point.
It's hard to see down there.
Okay.
Yeah.
I guess I should erase this already. Well, meanwhile, do you have any questions so far? It's half of the definition. But so the other condition is a recursive condition. Right? It's a recursive condition. If m is greater than 0, then every component of the algebraic boundary is itself a positive geometry, where the Ci greater or equal than 0 is equal to Ci intersected in my semi-algebraic set. So what I'm doing here, what are these? So Ci, I told you, are the components of the algebraic boundary, and the Ci greater than 0 are those parts on the algebraic boundary that intersect my semi-algebraic set. So for C1, I'm getting this. This is C1 greater than 0, and for ran out of colors, but for C2. This is C2 greater or equal than 0. right? So I'm intersecting my components of the algebraic boundary with the semi-algebraic set. I'm getting some new semi-algebraic sets. And then I want each of these to be again a positive geometry with canonical form. Being the residue of the big form on the component. Right. So, okay, let me illustrate here. What is the canonical form in this case? I claim that it is dx wedge dy y 1 minus x squared minus y squared. And we are going to look together, we're going to show together that this is a positive geometry. And the way of doing that is checking this recursive property. So this is a smooth form. It's a complex form. So x and y are points in the complex space, each of them. This is a smooth form on the complement of the algebraic boundary. So it has some poles, but exactly on the algebraic boundary. So it's smooth on the complement. And we should check the residues. For example, the residue along C1. Well, C1 is the vanishing of... I should tell you first what is a residue. I should tell you what is a residue. So if I take a smooth form on X, let's say, okay, let me do directly. Yes, you take local coordinates UZ, such that Ci is given by the vanishing of one coordinate. So you do a change of coordinates such that one component is exactly the vanishing locus of the coordinate. Then your form looks like dz over z, wedge sum omega plus beta, where this is smooth, holomorphic on all x. And then I can define the residue on Ci as omega. So I am identifying a singularity of my form, and I'm extracting that with this residue procedure. So let's see this explicitly. So for y equal to 0, the form is already in this nice form dy over y, wedge dx over 1 minus x squared minus y squared. So I'm taking the residue of this. So I'm removing this factor and obtain one form like this.
A minus maybe?
Yes, thank you. We switched the order. Right. So does this make sense? Yep.
Did you say what kind of singularities we like?
Thank you. Yeah. Right. I think that should stay. Yeah, I need. Thank you, Joris. I need logarithmic. And logarithmic means that for each component locally, I can reach this form. So if I choose a local coordinate whose vanishing is exactly one component, then locally I'll obtain this form. This assumption is what guarantees that. All right. Yeah, I'm seeing I'm very slow. So let me anyway show the other residue. for the example. So the other residue is along C2. The residue on C2. So for that, our omega is, we are going to change coordinates and go to radial coordinates to expose the pole. So if I write x equal to cos theta and y equal to sine theta, I can rewrite this in the following way. And now the pole on, so C2 is given by the vanishing of R. And this pole is now exposed. I have dr times 1 minus r. So I am left with d theta over sine theta. Right. Now, okay. Now you could argue that. So I said that you should have a rational form. You could argue that this doesn't look rational anymore in this coordinate. But you can write another set of coordinates which rationalizes this.
So C2 is R equals 1 or R equals 0?
Thank you. R equals 1. Okay. Did people get the handout? Or? Ah, fantastic. Okay. So are there any questions? Okay. Okay, let me.
This is a detail, but is there a 2 missing?
Yeah, it could be. Actually, maybe we can look at the further residue and we'll find out. So here is a 2 missing.
I think that
2t.
the 1 plus r gives you a 2, right? When you set r equal to.
Right.
Well, yeah.
Right. Although.
Okay, it doesn't matter.
Yeah. Okay. Okay. Good. And right. Maybe going back to the definition. So once you take, so we took a residue on C1, and then we want this residue to be the canonical form of this green region. And indeed, again, you can see that this is a regular form, except at the poles x equals 1 and x equals minus 1. And now you can further take residues at those points and show that there was a missing factor here, and show that the residues are plus minus 1. There should be actually. Okay. So, okay, you can already see that checking that something is a positive geometry is quite intricate if you want to do it explicitly in this way. Even if you are given a semi-algebraic set, and maybe you are given some way of constructing this form, to check recursively this definition can be quite involved. However, okay, there is a very natural way of constructing more complicated geometries from simpler ones, and this is by triangulating, because this canonical form behaves very nicely with respect to triangulations. So this is what I want to present. So for that, I'm taking a collection of semi-algebraic sets in some fixed ambient space X. Semi-algebraic and oriented. deal with this technical assumption. And then I say that this set, well, I want them to be positive geometries. Sorry, do I want to do? Yes. Sorry. Just get oriented. Let me just say that these are a collection of positive geometries, such that they interiors pairwise do not intersect, and their union is some set X X greater than 0. Right, and then the theorem that you can actually find in the first reference in the handout is that the canonical form of X greater than 0 is the sum I omega of X I greater or equal than 0. Right, and okay, I need also, so this is oriented. Thing has to be oriented. And so xi and xj must have compatible orientations. Okay. Right. So I can give you an example for this, for this construction. An example is the following. I'm supposed to do the opposite. So the example is the following. Say that I want to compute the canonical form. Okay, let me start with the triangle, actually. This is the line x minus y, and this is the line v of y and v of x. So the canonical form of this semi-algebraic set in coordinates is dx which dy over x y 1 minus x squared minus y squared.
They're squares, I think.
Sorry. You. And then I want to compute the form of this other one. So let's say this is x equals 1, x minus 1. This is y minus 1. The form of the orange thing, so is the white, and the form of the orange thing as 1 minus x, 1 minus y, minus x minus y. So we have these two forms. And then the claim is that if you add them up, you get the form of a new semi-algebraic set, which is the union of the two. And it's this bigger quadrilateral. Yeah, I should have used some numbers, but x greater than 0. And you can compute this. You can compute this to be this. Okay? So this is an example of how to triangulate more complicated spaces, in this case the quadrilateral, into simpler spaces, and use this additivity property of the canonical form. And then so in this way, for example, why are tilings for the amplituhedron useful? Because one can construct or can think of constructing the amplituhedron form using tilings. And if for tiles, then the canonical form is better understood. One can use this property to compute more complicated things. So in this way, one can prove, again in one, I think is a good reference, that every projective polytope is a positive geometry. So what is the idea? Is that every polytope admits a triangulation into simplices. So, right, it admits a triangulation into simplices, so it's enough with this additivity property to show that every simplex is a positive geometry. And the simplex, so if I take, for example, the standard simplex, which was denoted also previously by this Pm greater or equal than 0, so I can think of this, if I choose some coordinates, as all the xi greater or equal than 0. And then the canonical form, in this case, can be checked explicitly that it is just a wedge product of logarithmic forms on each coordinate. So this is a very, very specific choice of a simplex, but every other simplex in projective space can be reached by a linear isomorphism from the standard simplex. And then you can just push forward or pull back this form, and you get the canonical form of a simplex. So every simplex is a positive geometry. By triangulation and the property of canonical forms, every projective polytope is a canonical form. So now, how does the canonical form look like, even for polytopes? Okay, this is a way of constructing it. But let's say you have a very high-dimensional polytope, and you add a very big number of simplices together. How does your form look like in the end, once you put all the terms together in some sense? And there is a nice way of writing down the form, and is the following. So I'm defining a new object. It's called the adjoint hypersurface. So given a positive geometry, I can associate to it the adjoint hypersurface, which I'm going to denote by x. Well, this is really dependent on a positive geometry, as the vanishing locus of the canonical form. And this is inside X, the complex variety. So the canonical form is a rational form. It has some vanishing locus. Because this form is rational, the vanishing locus defines an algebraic variety inside X. Right. So how does the form, for example, of well, let's fix a polytope in PM. How does the form of projective polytope look like? Well, it's some polynomial Q, and then over the it has a bunch of linear factors, Li is of X, P of X. It has a bunch of linear factors. Each linear factor is cutting out a hyperplane, a facet hyperplane of the polytope, and then there is some polynomial in the numerator. Here I really want this to be full dimensional.
So Elia, what is the denominator? What's the product over?
The product is over linear factors. Linear such that this is a facet, hyperplane of P. And now, well, the adjoint hypersurface is really the vanishing of this polynomial in the numerator. So you can see that the structure of the form on the denominator is very simple, right? If you know the boundary structure of your semi-algebraic set, you know what you put in the denominator, the equations defining this boundary. But in the numerator, okay, you have something more complicated. What is it? And there is a very nice construction of deducing this, at least for the case of polytopes, that has been extended to some cases for the amplituhedron. And I'm gonna show you this with an example. And the example is the following: is a pentagon in P2. This example, P is a pentagon in P2. So a pentagon in P2 a pentagon in P2, so we have 5 lines cutting out the algebraic boundary, and we choose a region for our semi-algebraic set. Oh, yeah, sorry, I made it very small, actually. Let me try to scale it up here. To a bit better. Okay, so here's the scaled picture, and this is, well, this is P, pentagon. And now there is a notion of, it's called residual arrangement. So the residual arrangement characterizes all the components of the algebraic boundary that lie outside the semi-algebraic set. So we give you maybe this definition here on the left. So there is a subset of the algebraic boundary that is particularly relevant for determining this adjoint, and therefore the full form. And this is the following. So R inside the algebraic boundary of P, in this case, well, let me do more generally for any positive geometry, as the residual arrangement and is defined, so a component in, so every component in the algebraic boundary such that, now this looks a bit technical, but the complex dimension of Ci is greater than the dimension, the real dimension of the intersection with the semi-algebraic set. So concretely, what we are looking here, the algebraic boundary is the union of 5 lines, and the lines are of course part of the boundary, so they don't lie in the residual arrangement because each line intersects my pentagon in dimension 1. And that's exactly the dimension of the line as a complex variety. However, there are these points, which are intersection of lines, which have zero-dimensional intersection with my semi-algebraic set, and therefore are residual. So my residual arrangement is the union of these 5 points. On the other hand, you have other components like this one, which are really vertices. So these are also intersection of lines, but their dimension with the intersection of the pentagon is a point.
So maybe just to clarify, so here I is a multi-index. It's an intersection of components.
Yes. Let me see, maybe intersection. Let me drop this multi-index. This is the intersection. CI1, CIR, where the algebraic boundary is the union. So any iterated intersection of the components in the algebraic boundary. So what's happening here is that there is a theorem. The theorem, I think, in the second reference can be found, is that if so, you have a full-dimensional polytope. Full-dimensional such that, so here you have an extra assumption, such that the hyperplane arrangement defined by this polytope, or by the facets of this polytope, is simple. So simple means that every hyperplanes, sorry, there are no m+1 hyperplanes that intersect in a point. So this lives in M. Locally in Rm, and the hyperplane arrangement is simple if the maximal intersection of facets that is non-empty is M. Okay, this is technical assumption, and if this is true, then A is uniquely determined by the fact that it must contain the residual arrangement of P.
And it has the right degree.
And it has the right degree, yeah. So here, right, I forgot to say that because this form has to be defined on projective space, there is a certain relation between the degrees of this polynomial. So degree of Q must be equal to the sum, actually, to F minus M minus 1. So if you rescale simultaneously all coordinates in here, this full form should be invariant under the action of rescaling. So you'll pick up a factor proportional to the degree of raised to the power of the degree of Q, and below for each linear factor also a power, so as many as the number of facets. And then from the form you get this m minus the number of facets. So your polynomial in the numerator has a fixed degree. So by requiring that this surface has that specific degree and that it contains R, then this surface is uniquely determined. So going back to the example, we are asking, so how does the form of this pentagon look like? Well, it's in the denominator a product of 5 linear factors, and in the numerator, this is 5 minus 2 minus 1 is 2. So we must have a polynomial of degree 2 in the numerator. So we must have a conic in P2 that contains 5 points. And it's a very nice exercise to show that there exists only one such, if the points are generic. There exists a unique conic in P2, call it A, such that R, which is the union of these 5 points, is contained in A. Now this conic is determined by the vanishing locus of a polynomial, and it is exactly the numerator of the canonical form. So this is a different way of determining the form. I told you about triangulations, the very concrete and practical way. Also computationally, nowadays there are many programs to find triangulations even for huge polytopes. But what is the meaning of the full rational form you get in the end? I think geometrically is really this. That the denominator is easy to understand. The denominator is this other hypersurface determined by interpolation conditions with a residual arrangement. Yes?
Just a comment.
Yeah.
If you don't know otherwise, I think the simple assumption is not necessary.
Right, yeah. Yeah, you can extend this. If not simple, probably you can count with multiplicities.
Yeah, no, I know that Julian Weigert and
yeah.
is unpublished, but...
Yeah. I wanted to state something true in the literature currently, but I'm aware that with higher... okay, anyway, for who knows. Okay, so this is a story, and you can do similar things also for the amplituhedron. Now, I have to choose a bit what to say. I wanted really to... I didn't even mention to you the pictures that you have in your hand. So now I want to do that. So positive geometries, I told you, hopefully, what a positive geometry is, a bit in a sketchy way. And at least 2 ways on how one can compute the form of a polytope. But in principle, one can try this exercise also for other positive geometries. For example, in the second figure you have in your hand, or actually any of the figures you have, any of the subfigures in the first figure. You can also try to think on how to determine the adjoint, which is the red curve, in all the pictures. So the adjoint is a curve of a certain degree. So the semi-algebraic set is the lightly blue shaded region in each of the figures. The black curves define the algebraic boundary, and the red curve defines this adjoint hypersurface. And you can convince yourself that by interpolation conditions, you can fix it. Although there is a bit more. There is one weird example, which is this nodal cubic, which is singular. I cannot comment about that right now. But what I want to tell you is that you can see canonical forms as computing volumes. So this is very nice because it goes back to the original idea of Hodges. So Francesca mentioned Hodges. So Hodges was trying to find an argument for a magical cancellation between some poles in rational amplitudes and unequal force Young-Mills. And then he arrived in expressing the amplitude as a volume of a polytope, like as a single function. And this representation was completely free of any of these spurious poles, or poles that do not appear in the full amplitude, but appear in individual terms once you triangulate this polytope. So these are different description of the canonical forms. And for that, if you take a polytope, you choose a chart Rm in projective space. If you define the polar dual as the set of all y in Rm, whose scalar product, okay, you fix a scalar product, whatever you want to, maybe standard one, that satisfy this inequality condition with the original polytope. So this is called the polar dual. And then there is a theorem that I think also in the second reference in the paper is that in the chart, the canonical form computes really the volume of the dual polytope shifted by x. So let's do an example on the other board. Okay, this is going to be the simplest example, namely an interval between a and b in one-dimensional P1. Let's fix the origin here. So this is my positive geometry, my P. Now what is the polar dual? So I shift P by x. Did I put the right sign there? Yeah. Minus x. And here minus x. So this is P minus x in a chart. So sorry, it should be really R1. Now, if I take the polar dual of this, you can check that it's again an interval, and the interval is bounded by these two quantities. So b minus x becomes the lower bound with a minus sign and 1 over, and the same with the other endpoint. So this is p minus x dual. Now, what is the volume? So the volume is with respect to the Euclidean, it's the usual Euclidean volume with an appropriate normalization. So what is the length of this interval? The length is the difference between the endpoints. And this is indeed the canonical form of P. Why? Because it has exactly the singularities at A and B and the correct residues. If I take the residue over here, say on A, I get 1. So this is really the canonical form of the interval. Now, the rest of the pictures, unfortunately, I have much less time. But please come to me if you find them fascinating. The idea is that this works very nicely for polytopes, this formula. When you don't have a polytope, but you have a different positive geometry, say something curvy, which appears in figure 2 and 3, is this lightly blue shaded region at the leftmost subfigure. So if you take that P, in some cases you can still write the canonical form as some volume over the dual. But now the volume must be taken with respect to some probability distribution. So the probability distribution it's a function on, well, actually on this set. So it's a function on the polar dual. So the polar dual is the middle picture in figure 2 and 3 for each of the semi-algebraic set on the left. In the middle picture you have the polar dual, and on the right you have a plot of a probability distribution supported on the dual. So if you look at the graph, it's really supported on the polar dual, whose volume, so if you integrate that distribution on the dual set, gives you exactly the canonical function of the set. So this is a different view of interpreting, it's a different interpretation of canonical forms. And this is very desirable because it's really related to positivity. So I didn't also have much time to tell you this, but we are very interested in physics to understand properties, for example, of the amplitude, even of the tree amplitude as a rational function. And surprisingly, it is positive when evaluated in space, in kinematic space that we are interested in usually. And these positivity properties seem to be very much related to volume descriptions of these canonical forms, at least for the theories for which we have a positive geometry description. So this description really exposes the fact that both of this, so this probability is greater or equal than 0, this mu is greater or equal than 0, that the canonical form is non-negative for every x in P. This is an extra meaning of the term positive in positive geometries. And let me just super quickly tell you, there is a last picture related to actual integration. So once you have rational forms, you can think of integrating them on some other region. And if you do that for the blue shaded triangle in there, so that's a triangle, has a canonical form, very simple, you can write it down. You can integrate that triangle on the positive orthant, and you get a function that is very interesting for physics. It's the logarithm.
Parameters. You have parameters in the triangle.
Yes, it's a triangle that depends on z. If you look in the figure, z can vary between 0 and 1, so you can stretch this triangle. And for each fixed value of z, you can compute the integral of that canonical form on a positive orthant. And in this way, you trace out an interesting transcendental function for physics. So you can recover an interesting class of functions and deduce properties on them. For example, why is this function positive? Well, because it has this volume interpretation as increasing or decreasing the volume of the triangle. Okay, yeah, I was planning to say more, but feel free to come to me these days.